The San Andreas Fault is moving again. NASA satellites in 2025 spotted the ground twisting and rising across California, signs that the fault may be waking up.
New research suggests that two major West Coast fault lines could be seismically linked.
The San Andreas Fault, the legendary fracture that ripped the state apart in 1906 and 1989, has started to move in ways scientists have never seen before. In early 2025, NASA's Jet Propulsion Laboratory released new satellite data showing subtle but accelerating shifts in the ground across southern and central California. The crust isn't sliding, it's warping, twisting, and in some places, lifting. For decades, experts warned the big one was overdue. Now those same scientists say the Earth may already be preparing for it. The question is, are we? Chapter 1. The signs from space. NASA's InSAR satellites, capable of measuring ground movement down to a few millimeters, have revealed a pattern that's both familiar and frightening. From Parkfield to the Salton Sea, a 700-mile stretch of crust is creeping, shifting laterally and vertically at rates unseen in decades. But this isn't steady tectonic drift, it's erratic. Sections that were once locked are moving. Others that used to creep are now still. In some places, the fault appears to be inflating from below, as if pressure is building inside the crust itself. At first, scientists thought it might be groundwater changes, aquifer depletion, or post-rainfall expansion. But NASA's GRACE satellite ruled that out. The movement wasn't hydrological, it was tectonic. Microquakes recorded by Caltech's seismic array confirmed it. Small, rhythmic jolts clustered along fault junctions. Tiny pulses of stress echoing up from miles below. The same kind of movement that preceded the 1989 Loma Prieta earthquake. But this time, the pattern stretches across nearly the entire fault line. The San Andreas, long quiet, is beginning to breathe again.
Chapter 2. The pressure beneath.
To understand what's happening, scientists turn to 3D crustal models, digital reconstructions of California's tectonic underworld, peering into Earth's heartbeat. What they found was alarming. Deep beneath the Mojave and Central Valley, a pocket of viscous ductile rock, partially molten and hotter than expected, is rising slowly toward the fault. A slow boil beneath the desert. It's not magma in the volcanic sense, but it's soft enough to distort the plates above it. That distortion is now visible from orbit, the land itself bending under unseen pressure. Radar interferometry shows arching deformation patterns, like the crust itself is bowing upward, bending under invisible force. The center of that rise sits dangerously close to the Carrizo Plain, one of the most locked and overdue sections of the San Andreas. The fault's sleeping giant stirring once more. The implication is chilling. If that stress transfers upward, the fault could rupture not as one quake, but as a cascade, unzipping hundreds of miles in a single catastrophic chain. The fracture that could split a state. One geophysicist from NASA's JPL put it bluntly: the San Andreas isn't slipping, it's loading. That's worse. Chapter 3. The quiet zones start to talk. The silence along the San Andreas has never been true silence. It's the kind of stillness that hides motion too small for human senses, the calm that conceals chaos. Deep under the dry hills of Parkfield and the farms of Coachella Valley, instruments now record those hidden murmurs with unsettling precision. Arrays of broadband seismometers, some buried a kilometer underground, register vibrations 1,000 times fainter than the faintest earthquake people can feel. Beginning in late 2024, That background hum changed character, a whisper turning into rhythm. Instead of random noise, analysts saw coherent pulses repeating every few hours, faint, low-frequency tremors migrating north and south along the fault. Each pulse lasted minutes, sometimes half an hour, then faded. They followed the geometry of the locked fault line exactly, as if a zipper beneath the surface were sliding open a few teeth at a time. Laboratory modeling suggests these tremor trains occur when pressurized fluids seep into microscopic cracks, momentarily weakening the rock and allowing it to slip a few millimeters before locking again. Tiny fractures breathing under pressure. The effect releases no destructive shaking, but it redistributes stress into neighboring segments that have been quiet for generations. This is why scientists pay attention. The Nankai Trough in Japan and the Hikurangi Fault in New Zealand both produced identical patterns mere months before their last major ruptures, history echoing through stone. The rhythm of California's tremor bursts is now approaching that same cadence. To most residents, nothing seems different. Roads stay smooth, the air is still. Yet the instruments tell another story. A crust flexing, sighing, reorganizing its internal pressure. The Earth rehearsing its next move. The quiet zones are no longer quiet. They are communicating through vibration, sending low-frequency warnings up through miles of stone. Whether these whispers fade or crescendo into something larger will define the next chapter of California's history. The Earth has started to talk again. The only question left is who's listening.
Chapter 4. NASA's data confirms the drift.
Far below California's Golden Valleys, the boundary between brittle crust and the hot plastic mantle is shifting, the deep Earth stirring in its sleep. Seismic tomography from Caltech, USGS, and NASA's Jet Propulsion Laboratory now reveals something no one expected. A region of softened, partially molten rock rising slowly toward the San Andreas Fault system. It's not magma in the volcanic sense, it won't erupt, but it's warm and pliable enough to bend the colder rock above like a slowly tightening spring. Over the past few years, GPS arrays anchored across the Carrizo Plain and Mojave Desert have begun recording slight vertical motion, an inflation pattern spreading outward for nearly 40 kilometers, the land itself inhaling with tension. InSAR satellite images confirm that the surface there is arching upward by fractions of an inch each month. The cause is internal pressure. Dense, hot material creeping upward and expanding. This uplift concentrates stress on the locked portion of the fault, forcing the brittle upper crust to store more elastic energy than it can safely contain. The calm before a mechanical reckoning. It's the geological equivalent of bending a steel ruler. The greater the curve, the harder the eventual snap. Borehole temperature sensors reveal a parallel story. Gradients once stable for decades are now climbing, indicating that heat is migrating closer to the surface. The planet's fever slowly rising. Geochemical monitoring along nearby springs shows rising helium-3 and carbon dioxide, gases that leak upward when deep crustal rocks are squeezed. To geophysicists, these changes spell one thing: loading. The fault isn't relieving pressure, it's accumulating it. A locked section of the San Andreas acts like the weight of two continents pressing against each other with nowhere to go. A collision paused, not ended. When that boundary finally gives, it won't be a single jolt. It will be the release of years of stored compression in a matter of seconds. The Earth below California isn't quiet. It's flexing, swelling, and waiting.
Chapter 5.
The chain reaction. By early 2025, the changes were no longer confined to data tables. Entire landscapes across central and southern California were quietly rearranging themselves, as if the Earth were rewriting its own geometry. surveyors noticed that long-established benchmarks, steel pins anchored in bedrock, no longer matched their GPS coordinates. In some places, the difference was only a few millimeters. In others, several centimeters. To the naked eye, nothing looked different. But to geodesists, those tiny shifts are the footprints of enormous subterranean forces. NASA's InSAR radar and the state's continuous GPS network now show the crust moving in a complex mosaic of uplift and subsidence, a silent choreography of stone and stress. Parts of Riverside County are inching northwest, while sections of the Carrizo Plain are bending upward like a broad arch. Near Hollister, the ground is rising unevenly, creating micro-tilts that distort irrigation channels and drainage lines. Even the desert floor of the Coachella Valley has begun to ripple subtly, producing faint ridges where none existed 5 years ago. What alarms scientists is not just motion, but acceleration. The heartbeat of the fault quickening beneath their feet. The rate of deformation has doubled since 2020. Each millimeter of movement represents the crust storing elastic energy that must someday be released. The last comparable pattern appeared in the years leading up to the 1989 Loma Prieta quake, though on a much smaller scale. Field instruments now pick up micro-fracturing sounds, tiny acoustic pops from rocks cracking deep underground, like the ticking of a clock wound too tight. Chemical sensors show elevated radon and helium levels in wells along the fault, gases that seep upward when rock is stressed. Together, these signs describe a crust that's no longer stable, but adjusting under strain, like a wooden beam beginning to creak under weight. A continent holding its breath before the break. It hasn't broken yet, but the tension is measurable and growing. California's ground is not solid. It's a living surface, slowly twisting toward its next correction.
Chapter 6. The line between calm and catastrophe.
For decades, certain stretches of the San Andreas were thought to be locked in permanent sleep. Towns were built, roads paved, and pipelines buried over sections that hadn't trembled since the 19th century. But instruments tell a different story. Even the quiet parts of the fault are beginning to murmur. In early 2025, ultra-sensitive seismographs near San Bernardino, Parkfield, and Hollister began registering rhythmic, low-frequency tremors. They weren't sharp jolts, the kind that knock pictures off walls, but long, drawn-out vibrations that rolled through the crust like a distant engine. Their waveforms matched a phenomenon known as deep tremor bursts, slow-motion slips occurring 15 to 25 kilometers underground. Each burst releases as much energy as a small earthquake, but over hours instead of seconds. What makes these signals unsettling is their migration. They're spreading outward from historically quiet segments, connecting zones that used to behave independently. This suggests that pressure is no longer isolated. It's moving through the entire system, a continuous transfer of strain linking North and South California in one subterranean pulse. Geologists now suspect that fluids rising from the lower crust are playing a role. As these pressurized fluids infiltrate the fault, they weaken the friction that keeps it locked. Once that barrier drops, even slightly, neighboring sections can start to creep, setting off a slow chain reaction invisible on the surface, but recorded clearly in the data. The San Andreas is no longer a set of broken pieces. It's behaving as a single, connected structure again. For residents, that may sound abstract, but to seismologists, it means that when the next rupture comes, it could involve multiple fault segments moving together. A far more powerful and unpredictable event than anything in living memory. The quiet zones are awake, and the system is listening to itself.
Chapter 7.
The Domino Effect earthquakes are rarely isolated. Each rupture redistributes stress through the crust, tightening some zones while easing others. The San Andreas Fault lies at the center of an intricate network of secondary fractures that behave like interlocking gears. When one turns, the others feel it. In 2025, those gears began to move. Sensors along the Garlock Fault, which runs east-west across the Mojave Desert, recorded a subtle creep of about 3 millimeters, barely measurable, yet unprecedented in modern times. At nearly the same moment, instruments on the San Jacinto and Hayward faults detected a rise in background seismic noise, the kind that accompanies slow, deep motion. These systems are hundreds of kilometers apart, yet the timing lined up within days. Computer models later confirmed what many geologists feared. Stress transfer along California's fault web is occurring faster than expected. The physics is straightforward but unforgiving. When one locked fault segment resists movement, strain must find another pathway. The accumulated force slides sideways into neighboring fractures, priming them for failure. It's a domino effect written in stone. Historical evidence supports this. The 1906 San Francisco earthquake triggered activity along the Imperial and San Jacinto faults, just as the Ridgecrest sequence of 2019 reawakened faults 20 kilometers away. Now, the entire western margin of North America appears to be in motion. Deep tremors recorded under northern Baja California and Oregon's Cascadia subduction zone pulse in near synchronization, a pattern some seismologists interpret as regional coupling of tectonic stress. If true, the next rupture on the San Andreas might not stop at one break. It could cascade through multiple systems, producing a sequence of quakes that unfold over days. California's fault network is responding like a single organism, one heartbeat away from releasing centuries of strain.
Chapter 8. The NASA data they can't ignore. In late 2025, a joint analysis by NASA's Jet Propulsion Laboratory, Caltech, and the USGS quietly circulated among research institutions. The document was technical. Tables of deformation vectors, gravity field changes, and strain rate tensors. But its conclusion was stark. The San Andreas system is accelerating. For years, satellite interferometry had shown small periodic wobbles in California's crust. This time, the dataset was different. Combining InSAR, GRACE, and Sentinel-1 radar revealed a consistent trend. Broad uplift of the Mojave and Carrizo sectors, accompanied by subtle eastward tilting. The pattern mirrored what appears in numerical simulations just before a major shear failure. The ground wasn't only sliding, it was twisting, as if the state itself were being wrung like cloth. Gravity field measurements confirmed mass redistribution at depth. The crust beneath the transverse ranges was becoming slightly less dense, a sign that deep rock is deforming and fluids are migrating upward. Those fluids, once they reach brittle layers, can drastically lower friction along the fault, setting the stage for rupture. NASA's internal summary put it plainly. We are observing the transition from elastic loading to inelastic deformation in real time. For the first time, satellite readings and ground-based strain meters agreed to within a margin of a few microns. Proof that the movement isn't noise. It's genuine tectonic distortion. Behind closed doors, scientists debated how to communicate the findings without igniting panic. Publicly, the language stayed cautious. Phrases like heightened activity and anomalous uplift. Privately, many admitted that the numbers resembled those recorded before Chile's 2010 Maule quake and Japan's 2011 Tohoku event. No one can predict an exact date or magnitude, but the physics is undeniable. The San Andreas Fault is straining faster than the surrounding crust can absorb. The instruments can't look away, and neither can we.
Chapter 9. The warning signs multiply. By early 2026, California's surface began echoing what satellites had been detecting for years, the unmistakable signs of stress rising from deep within the Earth. The clues were subtle at first, changes in well water chemistry, odd surges in ground temperature, but together they painted a picture of a crust preparing to move. Hydrologists in San Bernardino County noticed groundwater levels fluctuating wildly, even in wells disconnected from seasonal aquifers. The explanation was simple and unsettling.
Stress-induced microfractures were opening and closing beneath the surface, altering subterranean flow. Meanwhile, methane and carbon dioxide seeped from new fissures along dry lake beds, a classic precursor to fault zone pressurization. At night, instruments in the Coachella Valley and Hollister recorded faint, rhythmic electromagnetic pulses. Though imperceptible to humans, these bursts often occur when rocks grind and generate piezoelectric currents. Essentially, the crust emitting its own electrical heartbeat. To geophysicists, it's a sign that the fault is nearing the end of its quiet cycle. Thermal cameras captured linear heat anomalies cutting across the desert floor, thin lines of frictional warming along shallow splays of the San Andreas. These aren't volcanic, they're mechanical. When locked rocks slip microscopically, they create heat, sometimes enough to register from space. The same pattern was documented in the Ridgecrest sequence days before its first rupture. Government agencies kept their public statements calm, no immediate danger. But the private data briefings told another story. Models showed that accumulated energy along the southern segment could release with a magnitude exceeding 7.8, comparable to the 1906 event, but impacting a far denser population. To scientists, every anomaly now carries weight. Taken alone, they might seem harmless. Together they form a chorus that's hard to ignore. The crust is changing tone, and the San Andreas is humming louder with each passing week. Chapter 10. The line between calm and catastrophe. California wears calm like a disguise. From the outside, nothing betrays the tension building beneath its surface. Blue skies, steady traffic, the low thrum of daily life. Yet the state rests on a fault line so charged with potential energy that a few seconds of release could rewrite its geography. Seismologists describe this period as the interseismic phase, the long, deceptive pause between major ruptures when stress accumulates in silence. According to USGS stress field models, the southern San Andreas has already reloaded to levels comparable to 1812, the year a quake leveled much of Mission San Juan Capistrano. More than a century has passed since the fault last tore end to end. By geological standards, that's an extended hold of the breath. Recent simulations from Lawrence Livermore National Laboratory show how fragile the balance has become. A rupture beginning near the Salton Sea could race northwest at 2 miles per second, unzipping more than 300 miles of crust in less than a minute. Ground shaking would last for over a minute in Los Angeles, long enough to topple unreinforced structures and rupture lifelines carrying water and gas across the state. The danger extends beyond infrastructure. Economic models estimate losses exceeding $200 billion, with ripple effects through power grids and ports that sustain the nation's trade. The line between ordinary life and catastrophe, it turns out, is only a few meters wide, the thickness of the fault itself. From orbit, California looks motionless, a stretch of gold and green stitched to the edge of the Pacific. But zoom in through NASA's instruments and you'll see the illusion break. The fault lines flicker with motion, each pixel of satellite radar revealing that the crust is alive and restless. By mid-2026, geophysicists noticed a new pattern emerging from the raw data. The entire San Andreas system was pulsing together. Minute uplift in the south coincided with subsidence in the north, repeating in a months-long rhythm that suggested the plates were shifting energy back and forth like opposing lungs. This isn't the random drift of tectonics. It's a coordinated, continental-scale adjustment. Field teams reported hairline cracks opening along rural stretches of highway near Carrizo Plain and San Bernardino, while groundwater sensors fluctuated in sync hundreds of miles apart. To scientists, these correlations mean one thing: coupling. The fault segments that used to act independently are now responding as one connected system. When that happens, small disturbances no longer dissipate, they amplify. For now, the San Andreas remains quiet, an orchestra tuning before the first note. Yet every reading, from InSAR radar to seismic strain meters, points toward the same reality. The next major release is inevitable. Whether it happens tomorrow or 50 years from now, the energy is there, locked between two continents that refuse to share space. If you've made it this far, remember that this isn't just a story about danger, it's about discovery. Scientists are finally seeing the Earth in motion with unprecedented clarity. Every quake, every tremor, every satellite scan brings us closer to understanding how the planet breathes. Stay curious, stay prepared, and make sure you're subscribed, because when the San Andreas finally moves again, the cameras will already be watching, and the story of California will begin a new chapter written in stone.